This is video 46 in the lecture on the design of reinforced concrete beams. This lecture deals with an exercise on pre-stressed concrete. This is example 4. An isostatic beam with a span of 15 meters is loaded with a uniform distributed load of 12 kilonewtons per meter in SLS characteristic. The initial pre-stress is 1100 kilonewton. The maximum eccentricity of the single radius tendon profile is 325 millimeters. Short-term pre-stress losses are 6% and the long-term 20%. We want now to calculate the stresses of the extreme fiber of a cross-section at 0.25 L of the support. So this exercise just deals with a random cross-section, and we are checking the stresses in the random cross-section. And this for two load cases, a load case on short term and a load case on long term. Load case 1, proper weight. The proper weight of the beam gives then a uniform distributed load of 5.9 kilonewton per meter. The short-term pre-stress losses is then 1100 times 0.94, and the 6% pre-stress losses is 1034 kilonewton. The curvature on the tendon profile is then L squared divided by 8E is 86.5 meter. The equivalent uniform distributed load caused by the pre-tensioning or by the tensioning is then P over R, it's 11.9 kilonewton per meter. And now we will work with a resulting distributed load. It means that we will subtract the two uniform distributed loads from each other, and we only work with the total distributed load, which is minus 6 kilonewton per meter. We are still in load case 1, proper weight. The vertical reaction due to the pre-stressing force is then equal to 89.6 kilonewton. The reactions in the supports is then the 89 minus the 6.01 distributed load, gives you 44.5, like it is stated here. It means that the bending moment at a position of 0.25 times the span, or 3.775 meters from the span, that the bending moment there is then in total 126.8 kilonewton meter. That's the bending moment at that section. So it means that in this section there is tension on the top fiber. Concrete cross section is 237,500. The W is this. Again, we are using the subtraction rule. On the top fiber, we have a tension now of the stresses on the top fiber is now the minus P1 over AC plus M1 over V. W, sorry. So it seems that a term is missing here, which is a term of P times E and so on. But we have calculated in the beginning, M1 is calculated with P times E inclusive. So we have taken the total bending moment instead of the single bending moment only from the external loads. So that's why there are only two terms in this equation. So this is compression and this is tension. If we put in some numbers, we will see that there is a net compression in the top fiber of 0.89 megapascal. In the bottom fiber, we calculate this is compression and this is also compression. So we have 7.81 compression in the bottom fiber. The bending moment is positive. It means tension on the top fiber, and compression is always in negative. So bending moment negative, then there is tension in the bottom fiber. And tension is calculated as positive. For load case 2, that's total load and long term. We look at the proper weight of the beam plus mobile load, gives you 17.9 kilonewton per meter. Long-term pre-stress losses is then 0.8 times 1100, is 880 kilonewton. The curvature of the tendon profile R is then L squared over 8E was 86.5 meter, and the equivalent distributed load due to the pretensioning due to the pretension is P over R is 10.1 kilonewton per meter. And the resulting distributed load, again, we are going to take the pre-stressing force together with the mobile loads. Then 7.7 is the resulting distributed load. So the resulting distributed load is now from top to bottom, because the effect of the mobile load supersedes the effect of the pre-stressed load, of the uniform distributed load coming from the pre-stressing force. The reaction on top due to the pre-stressing force is then 76.2. It means that the reaction is then equal to 134.5 kilonewton, the reaction force and the supports. And then we can calculate the bending moment at a section of 3.75 meters from distance from the support, and it gives us minus 163.9 kilonewton meter, and this means that there is compression on the top fiber because the bending moment is negative. Concrete cross section, that we know what it is, we know what W is. On the top fiber now, we have minus pre-stress divided by the cross section plus M1 divided by W, compression, compression. And it gives us in total of 8.2 megapascal compression. Bottom fiber, same formula, compression, tension. The stress at the bottom fiber is then 0.77 megapascal, and it means it's in tension. So bending moment positive, then the tension is in top fiber, compression is negative, and the bending moment negative, there is tension in the bottom fiber and tension is positive. So now you can perform a stress check on a pre-stressed concrete section. See you at next lecture.